The ninth in the series of simultaneous equations looks at the matrix inverse. So the previous video demonstrated that a simple algebraic solution for simultaneous equations involves a matrix inverse. Hence this video is focused on the definition of matrix inverse. We should note, however, that matrix inverse is only defined for square matrices, and we assume this throughout. So let's have a look at the concept of a matrix inverse. Let A be an n by n matrix, and let B also be an n by n matrix. Then B is the inverse of A if and only if these two identities hold. That is, A times B equals B times A equals the identity. Key point to note is that not all matrices have inverses. By that I mean not all square matrices have inverses. Let's look at this example then. Here's A, 1, 0, 2, 0. And I'm going to suppose that B is the inverse of A, and you'll notice that I've made the coefficients unknown for now, so B can change in order to make sure it's the inverse. Let's multiply A by B. So I've done that. There's A, there's B. I multiply the two out and I get this matrix here, AB in the top row, 2A, 2B in the bottom row, and B is the inverse of A if this product gives me the identity. So what does that tell me? Well, it tells me that A, this top left coefficient, has to be 1. It tells me that B, the top right coefficient, has to be 0, so A has to be 1, B has to be 0. It also tells me that 2A, the bottom left coefficient, has to be 0, and 2B, the bottom right coefficient, has to be 1. Now, if you look at these four conditions here, you will see straight away they are inconsistent. They give us contradictions. So here, A does not have an inverse. So we've given an example here of a square matrix which does not have an inverse. And the main point that you remember is not all square matrices have an inverse. Here's a different example which I won't dwell on. So A is 2114, and you can see B here, which involves fractions of a seventh. In this case, if you multiply A times B and B times A, which they've written out here, you'll find in both cases you get the identity. So in this case, B is equal to the inverse of A. Now, a matrix that has an inverse is called non-singular. A matrix with no inverse is singular. Let's look at some prerequisites then. So viewers are recommended to go through the resources on matrices 10 and 11 to remind themselves of some core concepts that we're going to use. These are: what is a matrix minor, what is the matrix of signs, and what is the cofactor matrix. And we'll go through these very briefly now. So defining a minor, and here for a 3 by 3 matrix. So a minor for a given coefficient is taken as the matrix with the relevant row and column removed. So let's have a look at finding A13. So A13 is this coefficient here. So I take out the column that A13 is in, I take out the row that it's in, and the matrix that's left is the minor A13. What if I want to do A22? Well, A22 is this one here, so I take out the row that A22 is in, the column that A22 is in, and the matrix that's left is the minor for 2, 2. We can do an example for a 4 by 4 matrix. So here, let's find the minor for A13, which is this coefficient here. So I take out the column A13 is in, I take out the row A13 is in, and the matrix that's left is the minor. Equivalent definition applies for higher dimensional matrices. Hopefully that's obvious. What about the chessboard of signs? So before defining cofactors, we need the concept of signs linked to matrix position. So what we do is we build starting with a positive in the top left, and then we make sure that we always toggle signs, so the adjacent ones are the opposite sign. So you see we go plus minus and so on. So that's why we call it a chessboard of signs, but always beginning with a plus in the top left position. And you come work out a formula if you want that ij is positive if I plus j is even and negative if I plus j is odd. So how do we define a cofactor? So a cofactor is the determinant of a minor with the sign taken from the sign matrix. So let's look again at this A13. You'll see we've taken out the row and the column. We've worked out what the minor is for A13. We then look at the sign for A13, which here is a positive. And therefore, the cofactor A13 is plus the determinant of the minor A13. And there's the case, it's 2 by 2 determinant. We can write it explicitly. What if we wanted to do A21? So again, we define the minor, A21, and then we look at the sign for this position, which here is a minus, and therefore the cofactor A21 is minus the determinant of the minor A21. What if you have a 4 by 4 matrix? Well, exactly the same principle applies. So here we're going to try and find the cofactor A23, so we start by finding the minor A23. So we cross off the row, the second row, we cross off the third column, and there's our minor. The cofactor then is the determinant of this minor with the appropriate sign. So if I do my chessboard of signs, plus, minus, plus, minus, plus, minus, I can see the appropriate sign I'm going to need is a minus. So the cofactor is given as minus the determinant of the minor A23. Finally, a reminder of how you might calculate the determinant. So we take our original matrix A, we define a matrix of the cofactor terms, and then we can do an expansion along any row or any column as follows. The coefficient A11 times the cofactor A11 plus the coefficient A12 times the cofactor A12, the coefficient A13 times the cofactor A13. So if we do that sum, we get the determinant, and you can see here I'm doing the expansion along the rows. I could equally do the expansion along any column. So all of those calculations will give me the determinant, and that was covered in the matrices vectors, the matrices videos. If you had a 4 by 4 matrix, you're going to get an analogous expression, except now we have 4 terms. And indeed, if you have an n by n matrix, you might just use this summation to make it clear. Okay, matrix inverse then. So what we've done so far is we've reminded you of the earlier definitions of cofactors and the determinant. And so now we're going to get to the final step, which is how do we use these to get the matrix inverse. And the key thing is this final step is almost trivial. So this is what we're going to do. Calculate the determinant, calculate the matrix of minus, calculate the matrix of cofactors, and there's a little warning here. In fact, you might want to find the determinant after you found the matrix of cofactors, but we're not going to dwell on that level of detail. So what next? Next, you take the transpose of the matrix of cofactors, and this is called the adjoint matrix. So you simply take the transpose, and then you multiply the adjoint by 1 over the determinant, and that gives you the inverse. So you can see the last 2 steps to get the inverse are simply a transpose and a scalar multiplication. A warning, however, you can see we're dividing by the determinant, so the inverse is only defined if the determinant is non-zero. Here's an example then. So here's my A matrix at the top. So the first thing I'm going to do is calculate the determinant. So I've done this by finding the cofactor A11, the cofactor A12, the cofactor A13, and then I've used my formula little a11 times cofactor a11 plus little a12 times cofactor a12 plus little a13 times cofactor a13, and I've found that the determinant is minus 26. So that's covered in earlier videos, so I've done it very quickly. The determinant is non-zero, so A is invertible. And again, a reminder, you may choose to find the determinant after you found the matrix of cofactors, and you'll see here we found the 3 cofactors before we did the determinant anyway. So next, calculate the matrix of minus, and then the matrix of cofactors. So you can see here I'm giving you the definitions of all the cofactors. So if we do them, maybe a few of them just to illustrate. So let's have a look at this A21. You can see that means second row, first column. So I will have crossed off the first column, crossed off the second row, and you can see what have I got left? I've got 1, 2, 0, 1. I found the determinant of that, and then I've looked at the sign, and the sign for that position is minus, so that cofactor is minus 1, 2. Alternatively, I could look at, for example, this third cofactor down here. So I cross off the third row and the third column, and what have I got left? 0, 1, minus 2, 3. So I find the determinant of that, and the corresponding sign for that one is a positive. So this is a very tedious step. I'm not going to pretend it's not. You've got 9 cofactors to find here. When you've done all the cofactors, you can build your cofactor matrix, and here it is. Now, if you want to check this slowly, what I suggest you do is pause the slide while you go through and check all those calculations by hand and make sure you're happy. Right, so in order to get the matrix inverse, what we've got to do now is find the adjoint matrix. And you remember, the adjoint is simply the transpose of the cofactor. So you'll see this minus 12 has gone down there because that's what the transpose does. This minus 2 has gone there, and so on. So all we've done is transpose the cofactor matrix to give us the adjoint. We already knew the determinant, we did that earlier, it was minus 26. So the inverse is simply the adjoint divided by the determinant. And you'll see I've just written it down here by inspection. Divide by the determinant, which is minus 26, multiplied by the adjoint. Okay, here's a problem that we might want to try ourselves. So if I define the corresponding A matrix for these simultaneous equations, you'll see I get 3, 1, minus 2, minus 1, 2, 3, 2, 1, 4. So what I need to do is say, okay, what are the cofactors? So let's start by looking at something like A11. So the cofactor for this is going to be the determinant of 2, 3, 1, 4. It's going to have a positive sign because it's A11, and so that's going to give me 8 minus 3, which is 5. What about A12? So here I'm going to get the determinant of minus 1, 3, 2, and 4, and I'm going to get a minus sign. So what do I get now? So minus 1 times 4 is minus 4, minus 6 is minus 10. With the minus sign added, I end up with 10. Now I can do this for all of the things, but I won't waste your time watching this video. So if you do that, the cofactor matrix you're going to end up with is 5, 10, minus 5, minus 6, 16, minus 1, 7, minus 7, and 7. And then if you want to calculate the determinant, you'll find the determinant of A is 35. And we'll just remind you, so that A inverse equals, I'll use a big brackets, it's the cofactor of A transposed divided by 35. And then obviously to solve for x, you just multiply by the corresponding B vector. Self-testing with MATLAB. Now, if you want to try a number of numerical examples to ensure you can do this correctly, I would encourage you to use tools like MATLAB. So define some arbitrary n by n matrices with a non-zero determinant, and then you can use commands like this to find your answers. So you can find the actual inverse using the command in for A, that's the easy bit. If you want to find the injoint, then you can trick MATLAB into doing it for you by writing inv A times det A. Inv A gives you the inverse, det A gives you the determinant. And if you want to find the cofactor matrix, you can just write the transpose of the adjoint. So the key point is you can create your own examples, see what the answers should be, and then try and replicate those on pen and paper. So in summary, this brief resource has introduced the concept of matrix inverse and given a simple procedure to find the inverse. However, the process of finding cofactors and the determinant are very inefficient in general, and hence this method is not recommended for large matrices. So what's going to follow in the following resources is some more efficient methods for finding matrix inverses and also solving linear simultaneous equations.